Hello and welcome to this class on computer vision basics. We will focus basically, as the name states, on digital camera parameters because this is a very broad area, as much as most of the areas that you have approached within this course. And we look mainly into some of the technology support and image and camera parameters. We'll start this class by looking into a broad definition of computer vision and also a broad definition of artificial vision areas. Then we'll move on to some basic definitions, also a little bit more in depth to the typical image processing pipeline. This happens within a vision camera. Then look into image parameters, both intrinsic and adjustable. Move on into basic optics, then to camera parameters and perspective views. Please look that camera parameters and image parameters are actually different things. And we'll end up with some examples of single image processing tasks. If we'd like to try to find a broad definition about computer vision, we could say that this is a general field that includes methods for acquiring, processing, analyzing, and understanding images. In this sense, an image can be either an image that corresponds to what we generally say is a visual field within the spectrum, so the images that we can see with our own eyes, or it can also be images outside of that particular spectrum. The fact is that computer vision applications are increasing every day, and robotics, of course, is one of the application areas where computer vision is getting more and more important. Basically before, computer vision is probably one of the most important sensors we can find in the systems. The reason why it's so important is because you can extract a huge amount of information about the surrounding environment of a robot, and in that sense you can get a lot of information that normally you cannot get from other kind of sensors, or you can get only by mixing different kinds of sensors. Looking again into vision applications, we could, for instance, talk about surveillance, we can talk about machine inspection, we can talk about medicine, of course, robotics. It can either be mobile robotics or non-mobile robotics, entertainment, of course, media, and so on and so on. One of the goals of computer vision is basically to make computer vision converge towards human vision or make it even better. And one of the ways to make it even better is by allowing us to look into images that our own visual system is not able to look into. That is, to look into areas of the spectrum that we are not allowed to see because they are outside of our vision field. Another way of defining artificial vision would be to define three different levels from the core that we normally call computer vision, moving outwards in terms of different levels of abstraction. So computer vision, as we already defined, basically define the techniques for image acquisition, extraction, characterization, and interpretation of information that can be gathered from images of the 3D world, that is the surrounding world. When we talk about computer vision for automation and robotic applications, it's quite common to call it machine vision. Moving outwards, we have a different level called image processing. In here, we are not dealing with acquisition or extraction, but we are actually processing the information where the input is a signal from an image. It can be a 2 or 3 dimensional signal, and the output that we get can be a transformation of this image or a set of characteristics associated to the image. Further on, there is a third level that we normally call artificial vision, which is today a very wide research field that includes all the sciences and techniques that allow the study and application of all activities related to the use and interpretation of an image. So in here we are actually trying to not only acquire an image, but also processing the image characterize and extract particular features from that image, recognize them, and then take a decision based on that knowledge. Given those broad definitions that we already seen, let's now move on into some basic definitions of what a computer vision system is, some of its technologies, and some aspects related to the representation of images. So the image you can see here is a simple representation of what we could call a digital camera or a computer vision system, let's say. So typically you expect to have some radiant power. Radiant power in this sense here is any source of waves that can be, for instance, light or visible light. This radiant power will go through a set of lenses that try to focus the image on the sensor itself. It can go or not through a mechanical aperture system that will reduce or increase the amount of light that goes directly to the sensor. Then it goes through a visual filter. As you can see, this visual filter is actually a matrix, and we'll look into it a little bit later. And through this filter, it goes directly into the sensor. In this case, the sensor is again a matrix. Each of the points in this matrix are actually called pixels or picture cells. And each of these small cells will acquire, during a certain amount of time, a certain amount of light. This amount of light, which is made of photons, is actually translated into electrons, is stored there so integrated there for a certain period of time, and later on it will be read out through a shift register, it will be amplified, and then it will go through a analog to digital processing system that in the end will provide serially to a computer system, for instance, the output that composes our final digital image. So if we look a little bit inside what we would call a image camera or a computer vision system, let's say, what lies as the basis for this system is a sensor. And as I already said, this is probably one of the most important types of sensors we can use in mobile robotics. There are currently two main technologies that can be used. One is called CCD for charge coupled device, and the other one is called CMOS for complementary metal oxide semiconductor. Basically, the differences among those are from the technological point of view, that is from the electronic point of view. CMOS is actually the technology that is used today for building digital systems or complex digital systems, such as computers, for instance. But CCDs, which are actually older in terms of technology than CMOS, is still important in the field of digital cameras. The considerations when it comes to select one or the other solution has to do with aspects such as speed, resolution, cost, final cost of the product, of course, signal to noise ratio, and other factors. We can look here in a very specific way some of the advantages of the CCD technology and some of the advantages of the CMOS technology. This first one produces a higher dynamic range than a CMOS camera, which means that you can create images that can differentiate more between dark and light images. They also produce a high uniformity image than the one you can obtain with CMOS, and also for the same temperature, let's say, produces a lower level of dark noise. Dark noise is basically the noise that appears on the image when there is no outside source of light. And this is called dark noise. Basically, this is thermal noise. And in the case of CCDs, the dark noise is smaller or lower than the one you can find in CMOS. Nevertheless, the fact is that CCD is the kind of technology which is used less and less because the overall cost of this technology is typically higher than the one you get with CMOS. So you would select a CCD technology for very particular cameras. If you require, for instance, very high resolution color images, where you probably would use not one sensor but three sensors, where the image will be splitted by a prism and projected in three sensors, with each one will have its own color filter. But aside from that particular aspect, and for the cost in particular, CMOS is much more common these days when you look into digital cameras. And that's because, first of all, it requires a lower voltage and lower energy. So you can power your camera from a power source that can deliver a lot less energy than CCD would require. It can allow you also a higher speed in terms of acquisition and transference of information than you can get from CCDs. The complexity of the system itself that relies behind the scene of the sensor is also much lower in the case of CMOS than in the case of CCD. And there is another plus, which is also very important, is that since CMOS is also the technology used for building digital computers, this is a very flexible solution in terms of complementary hardware that can be built inside the camera itself, which means that you can build a computer inside your own camera using the same technology, which means that the camera can produce an output which is already a pre-processed form of image, and in some cases can already produce information that is also already a characterization of some particular aspects of the image. In some cases, you can even classify objects within an image with such a kind of camera. These particular kinds of cameras that have some significant computer power inside are normally called intelligent cameras. Apart from the sensor itself, so either CCD or CMOS, if you look into the world of digital cameras, you'll end up with a huge amount of different solutions depending on several different aspects. So depending on the application you have, depending on the amount of money you have, depending on the quality of the image you want, etc., you can select from very different cameras with costs that go from just a few euros to maybe tens or hundreds of thousand euros. So basically, what are the differences you can find in these all families of cameras? First, the kind of interface. You can select cameras which interface to computer through FireWire. This is less and less used these days. That can, for instance, connect through Giga Ethernet, through Camera Link, through USB 3, for instance, and there are more than this. Also, it depends on the scientific usage. There are cameras for very high resolution, for instance. Cameras allow you to get images with a significant amount of pixels, and in fact, resolution has not only to do with the number of pixels you get in an image, but the number of pixels per area defined in the sensor. So let's say the number of pixels per square centimeter. Or you can have, for instance, cameras for a very long exposure time, such as those that are used in areas as people that work with the stars. So in astronomy, for instance, you can require very, very long exposure time, which on the other hand implies necessarily that the dark noise is very, very low. Otherwise, what happens is that the dark noise will build up upon the time and will destroy the image itself. You can also find cameras for a very high speed. an exception of 1000 frames per second. You already probably saw videos at very, very low speed taken by these kinds of cameras. You have also cameras which are not a matrix, but actually only a single line, so only a vector. And it's quite common in cameras like this to be able to get something like 10,000 lines per second. You have cameras for getting information in 3D, so you can get information typically on a plane with 2 dimensions plus a third dimension, which is the depth. You can have cameras for looking into the infrared area of the spectrum, for instance, between 8 and 14 micrometers, which is really outside the area where our own vision can look into it. You have cameras which are multispectral, so they are built to acquire image in different areas of the spectrum, depending on the application that you are looking into. There are some very interesting areas related to robotics for multispectral cameras. For instance, when we talk about robots that are on the field looking into the quality of fruit, one of the aspects that normally we look into is the aspect of the fruit itself, but seen in different areas of the spectrum, and that give you different kinds of information that you can collect from the images. And you also can have, for instance, high dynamic range cameras, and sometimes this is done using a prism and 2 sensors. One of the sensors is focused on areas of the image which is very dark, and the other sensor is focused on areas of the image where you have higher intensity of light, and this will provide you with a high dynamic range image. So once we have looked into some of the basic technologies of the sensors and the large variety of cameras you can find in the market, it is now time to bring up the concept of image and which are the main elements that can constitute an image, and in this case an image considered to be a color image. And there are basically 2 important components. The first one is luminance, and this is important. I think this is a general concept, and it is important for everyone to understand the meaning of this. The common definition of luminance is the measurement of the photometric luminous intensity per unit area of light traveling in a given direction. So basically, luminance is the amount of energy that is taken into a vision sensor by the light that strikes that vision sensor. So it has to do with the level of energy. Of course, the higher the level of energy, the brighter the image will be. The lower the level of energy, the darker the image will be. So luminance is normally used to describe the amount of light that goes through or is emitted from a particular area. Of course, because luminance can be measured from the acquisition system point of view, but you can also use luminance to define the amount of light which is emitted from a source. So if you talk about a light bulb, for instance, you can also define the luminance emitted by the light bulb. And the luminance is defined from that amount of energy that falls within a given solid angle in space. The SI unit for luminance is candela per square meter, and in computer graphics system, the unit of luminance is called stilb, which is equal to 1 candela per square centimeter, or around 10 kilos candela per square meter. These units are not particularly relevant for the kind of knowledge you have to acquire in this class, but at least give you an idea of the concept and how it is defined in terms of units. Apart from luminance, chrominance is the second parameter that, together with luminance, will provide us the general concept of a color image. In fact, chrominance is a basic numeral, so it has no units, and it describes the way a certain amount of light is distributed among the visible spectrum. So if this is a single numeral and has no units, it means that he has no relation with luminance. Chrominance and luminance complement themselves, but information of luminance has no chrominance associated, and information of chrominance has no luminance associated. So, for instance, a black and white image has a balanced distribution of energy among the visible spectrum. In the case, for instance, of matching the bandpass characteristics of our human visual system. In that case, this means that when viewed by a human, a black and white image has no color information. I think this is common sense, which means that chrominance or color information in that case is zero. And if we are looking into a black and white image, the only kind of information we have is luminance. That is the amount of energy that strikes each of the pixels that are contained within the image. Therefore, chrominance, which is the second parameter, has no luminance information. This is important, but it is used together with the luminance to describe a colored image defined, for instance, by an RGB triplet. RGB, I think everyone knows what it means red, green, and blue. And we use this source of information for color. It's quite common in computers, for instance. And in fact, any RGB triplet, that is, the triplet means three values, one for red, one for green, and one for blue. Any RGB triplet in which the values of each of the three components is equal, that is, if red is equal to green and equal to blue, has no chrominance information. Means that the distribution among the spectrum is exactly the same for red, green, and blue. So if we want to extract, for instance, a black and white image from a color image, what we have to do is to make some sort of transformation in order to ensure that for every pixel, the value of red, green, and blue is exactly the same. What you can see down here in this image is the spectrum, let's say, from very long wavelengths, that is very long wavelengths means very low frequencies, to very short wavelengths, which means very high frequencies. And here you are in the area of cosmic rays, then gamma rays, X-rays, ultraviolet, and then there is this small area here, which is expanded down there, where we consider to be what we call visible light. That is the kind of light that human eyes can perceive. So this starts on the high frequency side on close to the 400 nanometers, that is violet, and beyond that we call ultraviolet. Then we move down through blue and green, yellowish until red, and then there is an area below the 700 nanometers where we call the infrared area that our eyes can also not see. So this is the very small area of the spectrum that our eyes can perceive. Most of the CMOS or even CCD sensors that we use in normal cameras can see at least this area of the spectrum, and most of the times also a little bit more in the infrared area, which means that with a normal sensor, image sensor, you can actually perceive more information than the one we can perceive with our own eyes. So in the previous slides, we already defined two ways of defining a color image. We talked about RGB triplets as red, green, and blue, which means that you can define a pixel, a color pixel in an image by applying values to each of these three components, red, green, and blue. But we also talked about luminance versus chrominance. And luminance versus chrominance is defined as the model YUV. In this case, Y stands for luminance, U and V stands for the two chrominance components. In fact, there are several ways of representing what we call color spaces. There is different ways of representing luminance and chrominance. From the RGB triplet, which is quite common because normally we define images in particular in computer graphics by using RGB. If we have or we start from RGB triplet, we can obtain another triplet, YUV, in which luminance and chrominance can be separated by these three equations. So luminance based on RGB will be the result of a weighted sum of the three components. R will be multiplied by WR, G will be multiplied by WG, and B will be multiplied by WB. The sum of these three weights, W, will add up 1. And you can see down here exactly their values. So WR, so W for the red will be 0.299, WB will be 0.114, and WG will be 0.587. If you add up these three numbers, you'll come out with 1 as expected. In fact, it is curious that the way each of the three components in RGB produces the final luminance value is not equally distributed. In fact, the green component will have the majority of the impact in the final luminance, while the red component will have an intermediate value and the blue component will have the lower one. These three numbers actually derivates from the general model of the human visual system, and it had in the past a significant impact on the ability to develop a television color system that could be compatible with the original black and white television systems. So the way we obtain luminance from these three elements is by weighting in this way. The reason why the green one is higher than the others is because our own vision system have a higher response to the green region of the spectrum than the response in the red, and our lower response in terms of spectrum will be in the region of the blues. And having obtained the Y, and this is basically the equation from which you can get a black and white image from an RGB image, you can also extract the chrominance components, which are called U and V. And U and V can be obtained from the B, which is the blue minus Y, and the red minus Y, in which Y is the luminance, multiplied by these two factors. Please do not forget that U and V has no information about luminance. This is only about color. So if I create an image only based on U and V, this image will have no luminance, in terms of luminance will be completely flat, but will have different colors depending on the components of the RGB pixels. Of course, these operations can be or are symmetrical, which means that if you get an image based on a YUV components, you can obtain another representation based on RGB. So you can intermute between these two ways of representing information. Another interesting fact is that, and it has or is related to the way our human vision system functions, is that our resolution perception, that is our ability to detect differences in space, is higher when it comes to luminance than when it comes to chrominance. The resolution is normally measured as an angle. That is, if I have, for instance, a sinusoid represented in space that goes more bright and then goes down to a darker zone and then again more bright, you can increase the frequency in space to a point where you are no longer able to distinguish between darker and lighter zones. So the maximum visual resolution is defined as an angle which is based on the distance between two maximums and the distance from your visual system to the point that you are observing. And one interesting thing is that our our spatial resolution in terms of luminance is much higher than in terms of chrominance. We don't require the same resolution, physical resolution in space for color as much as we require for luminance. This means that in some situations, some visual systems will take advantage from that, and for each pixel, it will send the computer a Y value, but it will only send one U chrominance value for each 4 adjacent pixels, and only one V value for 4 adjacent pixels. This implies that you can reduce the amount of information that you have to transfer between the camera and the computer, and therefore you can reduce the overall bandwidth required by that factor. Of course, this is only relevant in the situations where the target final image is the human visual system. If the idea is to process the image itself, this may or may not be a good approach. As I said before, there are many different ways of representing color spaces. The one you can see here is the RGB space we already mentioned. So basically by mixing different values of red, green and blue, you can obtain different colors. For instance, if you mix a pure green with a pure blue, you obtain a cyan color. If you mix a pure blue with a pure red, you obtain a magenta color. If you mix a red and a green, you obtain a yellow. If you mix the three of them, you obtain white. So this is quite typical in what we call emissive color systems, which is the case, for instance, of computer displays. There is also a complementary system which is used for reflective systems, such as the results of printouts. In that case, what we use is not an RGB system, but a CYMK space. Because when we look into a print image, what you are seeing is not the light that comes from the image, but the light which is reflected from the image. Basically, the image is illuminated from outer source. It absorbs part of the spectrum and reflects the remaining spectrums. In that space, we use the complementary colors for RGB, which are magenta, yellow, and cyan, hence CYM, but there is also a problem that there is no way of mixing the three of them to obtain a perfect black. So normally printing systems that use CYM also include black ink so that you can produce correctly a black image. Here on the left you can see what would be the UV plane. I remember that U and V are chrominance components. So if we create an image only based on all the combinations of U and V, what you would see is something like this. As you can notice, there is no luminance in this image. What you can get is only chrominance information. There are other color spaces which are also very interesting, namely because they are closer to our own way of perceiving color than the ones that we describe or use when we work with RGB or with CYM. For instance, one of quite common way of representing color is called HSV space. An HSV space is represented as cylinder, like you see on here. In fact, all the other three spaces that you see are variants of the same. And HSV stands for hue, saturation, and value. Hue is represented as an angle along the outside of this cylinder, so a circumference, and hue represents chrominance, color. So basically it will start around the red and then goes around all these colors and goes back to the starting point. So you can define hue as an angle typically between 0 and 360 degrees. Then there is S, that stands for saturation. Saturation is a concept which is easy to understand because it's basically the amount of white that you mixed into a pure color. For instance, red, as it is in here, is a completely saturated color. But if you mix a little bit of white with red, then you get pink. And pink is a non-fully saturated color. So if you are here on this area, you start by red on the outside, where the fully saturated colors are. And if you move inside, you are actually mixing more and more white. And in the center, there is no color. So in the center, you have a simple black and white information. So you move through different levels of pink, moving into white. And this is interesting because this is the way we can easily describe colors. Value has also a relationship with luminance. It's not a direct translation of luminance, but it has also a equation that allows us to get value from luminance and vice versa. So typically on the bottom of the cylinder, we have a very low value, that is a dark image. And when we move upwards, we are increasing the value, that is, we are increasing the level of the luminance. An alternative to this one is this one here, which is called HSL instead of HSV. And the difference is only that instead of using value, here we use lightness. And lightness, in fact, is closer to luminance, because the idea is that if you are in the top of lightness, you have no color because all the sensors are fully saturated, which means that, for instance, in an RGB system, all the components R, G, and B will be at this maximum. And we decided, or we saw before, that if a triplet has the same value for R, G, and B, then you have no chrominance, which means that in the case, the top of the cylinder will be completely white, the bottom of the cylinder will be completely black. And here are also different alternatives for representing color spaces, and you can convert between all of them in order to manipulate information according to the best color space depending on the application you have. Although we haven't discussed that in detail, one important thing is that the image sensors that are used today, either CCD or CMOS technology, are actually able to grab light energy only. And this is done through a conversion process from photons to electrons, which are then trapped either in an array of potential wells, this is the case of CCDs, or in an array of capacitors. Which means that the final image that is gathered in the sensor is actually an image that has only luminance information. And therefore, it is important to know, okay, but if our sensors can only acquire luminance information, how can we get color out of that information? And the way we do this is by placing color filters in front of the pixels. And this represents one of the pixels, that is one point of the sensor. In this case, we are assuming that we have light with components on different areas of the spectrum, so blue, red, blue, green, and red information. But because of this red filter, only the red information will be trapped inside, and therefore this particular pixel will be used only for acquiring luminance on the red area of the spectrum. If you place a green filter in front of a pixel, then this means that this particular pixel will only get information of luminance in the green area of the spectrum. And finally, if we put a blue filter in front of the pixel, you gather information of luminance only on the blue area of the spectrum. The most common way of building up these filters in front of the sensor is by creating what we call the Bayer pattern. A Bayer pattern is the repetition of these 2 by 2 square pixels. So these 2 pixels on the diagonal are green. That means there are green filters in front of them. There is one blue here and one red there. The reason again why there is two green and only one red and one blue is the same that we used before to explain why the green color has a higher component when you obtain the luminance from the color or the color triplets RGB. So for each 4 pixels, 2 of them will collect information on the green area of the spectrum, one will collect information on the red area of the spectrum, and the other on the blue area of the spectrum. And this is one of the reasons why the chrominance information typically is gathered together. There is, out of these 4 pixels, you create a U and a V component, and you send a single U and V component for these 4 pixels, reducing therefore the spatial resolution for color. The luminance resolution can be modeled by the information gathered on each of these 4 pixels. So basically, based on this one and on its neighbors, there is a weighting factor for this, and therefore, from the luminance point of view, can still use the original resolution that you can see over here. So the patterns in terms of filtering is similar to what you can see here from view from the top. In this case, you are looking from the side. And this is called a Bayer pattern and is almost universally used in the acquisition of color images. If you require a color image with a very good spatial resolution, there is one solution. Normally it uses CCDs. So the incoming light will go through a prism. This prism will deflect the light in 3 directions. Each one of these directions go through a single red, a single green, or a single blue filter and strikes a full CCD sensor. That is, in a camera such as this, there will be 3 different sensors, one only for green, one only for red, and another one only for blue. Of course, this is a much more expensive camera than the normal cameras you use in our day-to-day work, let's say. Now that we have a basic knowledge on the kind of technologies available for vision cameras, talking about CCDs and CMOS technologies, the sensors themselves, we also discussed some of the basic parameters that contribute to an image color. We discussed a little bit about color spaces. Now it's time to move on into the typical image processing pipeline. And it is important to state that this pipeline is still inside the camera. So it has nothing to do with the image that is further on processed by a target computer. In this pipeline, we'll look into some of the parameters of the image. Some of them will be intrinsic, some of them will be adjustable, and some of them will be both intrinsic and adjustable. So the image processing pipeline is something similar to this scheme you can see in the downside of the slide. A typical image processing pipeline can be performed based on YUV output of the sensor, so with luminance and chrominance components, or you could do the same basically on a sensor that directly produces an RGB image. It's not relevant if you are working on one color space on another. So this should, on the other side, be understood as a mere example because this pipeline can be less or more complex depending on the camera that we are talking about. Depending on the system we are talking about, there can be less or more image parameters that are available for the user to control. And also some of these parameters, namely the brightness, the contrast, and the saturation, are also intrinsic to the original image. Means that the original image already have a certain level of brightness, a certain level of contrast, and a certain level of saturations. Nevertheless, even being intrinsic, all these 3 parameters can normally also be externally controlled parameters, which means that you can later on, if you want, change the value of the saturation of the image, change the value of the brightness, or change the value of the contrast. As you can see here, there are other blocks namely sharpness, gamma, white balance, which are part of this pipeline. So we will discuss in a little more detail each one of these elements. So the first parameter, in this case we are discussing it as intrinsic image characteristic, is called brightness. Please do not confuse brightness with luminance, because luminance has to do with the amount of energy which is stored in each pixel, while brightness represents a measure of the average amount of light that is integrated over the full image during a certain amount of time that we call exposure time. This exposure time, on the other hand, can or cannot be externally adjusted. This means, in fact, that exposure time is the period of time during which you start acquiring a new image, that is, you start integrating information on each of the pixels, and when this exposure time ends, you get that image out of the sensor, you clear up the sensor and start the acquisition of a new image. In this way, depending on the exposure time, you can have more light energy gathered on the image or less gathered information on the same image. Exposure time also have an impact on the maximum frame rate, that is the maximum number of images per second that you can get from a camera. Of course, that if the brightness is too high, you can come out to a situation that you call overexposure. In that case, probably part or completely the full image can be saturated in the sense that all the pixel will simply become white. So if there is a significant amount of light, that is, if the luminance is high, and you expose the sensor for an exposure time which is long, then the brightness will simply saturate, which means that you'll get out a completely completely white image in this case. On the other hand, if you are in a very dark environment, for instance, and you have a very short exposure time, it means that you don't give time enough to actually gather relevant information of luminance on each of the pixels, which means that probably in the end you'll simply get an underexposure image, which is a very dark image or even a simply black image. But brightness, apart from being an intrinsic parameter of the image, can also be normally a controllable parameter, which means that you get here the brightness characteristics of the image, but you can actuate on this model to change dynamically that brightness level. If you consider this small graphic here, the central line is the basic transfer function, where on the x-axis you have the input image, on the y-axis you have the output image. The normal non-manipulated brightness information will have the transfer function you see on this line. If you want to increase the brightness, basically what you do is to add a certain constant to all pixels of the image. So you keep the same derivative, the same gain, let's say, you simply add a constant. If you want to turn the image darker, reduce the brightness, you simply subtract a certain constant and you change the transfer function, which is still parallel to the original one, but now at a lower level. So in the case of this central image you can see here, this would be the normal image acquired by the camera. On the left, you would see the same image when you reduce the brightness, and the transfer function is this one. On the right, you will see the image that acquired when you increase the brightness. And depending on the intrinsic parameters you are using, it may be interesting to change slightly the brightness up or down to correct or to adjust those areas of the image that you are more interested in. Another very important parameter, in this case an intrinsic one, is called contrast. It is important to say that there is not a unique definition of contrast, but one of the most used ones is that contrast is the difference in terms of luminance, or maybe in terms of color, along the 2D space that makes an object distinguishable from another one. In visual perception of the real world, contrast is also determined by the difference in the color and brightness of a particular object and other objects within the same field of view. And therefore, we can say that contrast, as for instance in terms of luminance, has to do with the rapid or slow variation of luminance across or along a line on our image. The faster and higher the luminance changes along the space, the higher the contrast is. And it is also common to state that the maximum possible contrast of an image is denominated contrast ratio or dynamic range. So contrast in this sense, as well as brightness, is also an intrinsic characteristic of the image. But as you'll see in the next slide, we can also manipulate contrast by activating on this particular block of the pipeline. Before going there, however, let's also create a different perspective of what contrast may mean. And one of another possible definition of contrast is given by this expression, is the ratio between the luminance difference in luminance, divided by the average luminance. And one interesting fact is that the human eye contrast sensitivity function is a typical band pass filter, which means that we cannot perceive contrasts above a certain frequency in space, with a maximum at around 4 cycles per degree. Remember that we already talked about that. Say if we think about our visual system as the center of a circle, and we have a projected image on the periphery of that circle, then if we have variations of 4 cycles within 1 degree, this would be the maximum sensitivity in terms of contrast that our perception system will hold. This will reduce to both sides of that maximum. So if we reduce the number of cycles per degree, our perceptions of contrast will also diminish. If we increase, the problem is our resolution is not good enough, and because of that, our perception of contrast also will be smaller. This means, in fact, that the human visual system can detect lower contrast differences at 4 cycles per degree than at any other spatial frequency. This may be interesting and important in those applications where the final image is dedicated for the human visual systems. Of course, there are many other applications, namely in robotics, which the target result of the image is not a human system, maybe a robotic system, and therefore this may not be in that particular context of any importance at all. But as I said before, contrast can not only be an intrinsic image parameter, but also a controllable parameter, which means that you can externally change the contrast of an image in the same way that we did with the brightness. So going back to our transfer function, which is again the original transfer function is this line. The inclination of this line of the gain is 1. And the difference here is that if you want to increase the contrast, you don't add up a constant, but you change the gain, or you change the derivative. If you increase the derivative, which is the case of this line, then you increase the contrast. If you decrease that derivative, then you decrease the contrast. Looking again, this image would be the original contrast image with intrinsic parameters. And on the right, you can see the image that results by increasing the contrast by using this transfer function. And you can see that there is a sharper regions between white and dark areas of the image. If you reduce the contrast by reducing this angle, what you get is a smoother image in terms of variations of white and black, or variations of color, let's say. And therefore you can actually mix variations of brightness with variations of contrast to starting from a certain image, obtain an image which is better for your particular application. We now move into this particular block here, white balance. You can see that the white balance has as inputs the chrominance components, U and V, and generates two new chrominance components. What's the idea behind the white balance? The problem is then that when you are obtaining an image on a certain environment, the illumination source can vary significantly. For instance, if you are outdoor, the primary source of light will be the sun, and the sun will have intensities along the spectrum which differs, for instance, from the light source that you can get from a light bulb inside a room, for instance. And since you now are familiar with LED-based lamps, you know that one characteristic of these LED-based lamps is what we call the temperature color. The temperature color again has to do with the way the intensity of the energy produced by the lamp is distributed across the spectrum. The result is that if you illuminate the same scene with, say, sunlight and an inside lamp, the resulting color of the resulting colors of the same scene will be different because of that different distribution along the spectrum. The objective of the white balance is to compensate for that fact. It's called white balance because you try to adjust or readjust the U and V components so that a gray piece of paper, for instance, will show gray independently from being illuminated from a yellow lamp, a yellow or yellowish lamp, or from the sun. So white balance is basically try to render specific colors in a correct way. This general method is sometimes also called gray balance or neutral balance. So this is quite important, in particular when you want to process the images to extract areas of the image with the same color. Of course, that if you change the source of illumination, that particular color will show differently depending on the light illumination source. And if you don't compensate for that with the white balance, you won't get the same results while processing the image. Therefore, white balance is actually a very important part of this pipeline sequence in order to obtain an image that can be processed correctly in terms of chrominance. In this slide, you can see a simple image where the concept of white balance should be apparent. Here you can have an image acquired from the same scene as the other two images. In this case, the white balance is not correct because depending on the source of illumination. On the right side is also with a different source of illumination is also not correct. This clearly the image, the ground should be green, is also bluish. The ball should be orange, now is yellow. On the left side the ball is more like magenta, and the blue will tend to be greenish, let's say. And by adjusting the white balance you can compensate for these effects and move towards the central image, which is the original one that we'd like to have in order to process and eventually segment correctly the different colors you have on the image. Another intrinsic parameter you have on an image is also the saturation. Saturation has to do, if you remember back when we talked about color spaces, the amount of white you mix into a pure color. White actually is an equal distribution of energy along the spectrum, while a pure color is a single line in that particular spectrum. So if we're talking about saturated images, we are talking about images where all the pixels belong to a single stripe on the spectrum, while low saturated images mean that there is some white mixed into it, and therefore the image will be more equally distributed along the spectrum. So the most purest the color is, the most saturated we say it is also. The top example for this will be the laser light. Laser light is a single line on the spectrum, is a pure light and saturated light. So if light intensity declines, then as a result, the saturation also tends to decline. A completely non-saturated image, which is basically a black and white, has a spectrum distributed that matches the human eye spectrum sensibility. Saturation is sometimes also defined as the amount of white you have blended into a pure color, which is basically the first definition that I gave when I talked about the HSV color model. Again, saturation can also be a controllable parameter, which means that externally you can define the amount of saturation you want to introduce into an image. So if we assume that the original image is this one, which is own saturation, we can oversaturate the image. This is the case on the right, by manipulating the gain on the chromatic components. If you reduce the gain of the chromatic components, you then reduce the saturation. In this case, this is an example of a low saturation image of the original one. And if you move the gain down to zero, what you get in terms of chrominance, of course, what you get is actually a black and white image of the originally colored image, as you can see here. Finally, in our pipeline sequence, I would like to refer gamma, because gamma is actually very important, normally or namely in photography. And basically gamma is a type of a correction which is the result of the application of a nonlinear operation, a nonlinear function over the different parameters, contrast, brightness, and saturation. In the simplest way, gamma is defined by a power law expression of this form, you can see here, where normally A is typically 1, and inputs and outputs are typically in the range 0 to 1. We saw before that, for instance, for the brightness, the typical transfer function will be a line with derivative of 1. And with gamma, we can change not only the derivative, but transform that linear transfer function into a non-linear transfer function. These, for instance, are examples of gamma corrections applied into images. And why are these corrections important? Assume that for a particular application, you are quite interested in the darker areas of the image, but it's not really important the brighter areas of the image. The original transfer function will be this dotted line over here. If you want to take more, if you want to increase the contrast in the darker area of the image, basically what you do is a gamma correction of this size, which means that you increase the gain on the darker size and then decrease, because the gain is the derivative, you decrease this derivative on the brighter side. So an example of a situation like this would be to start from this image, which is dark, and then obtain this one by applying this gamma correction. On the other side, for instance, you can apply a gamma correction which is different. This has an exponent of 1 divided by 2.2. In this case, the exponent is 2.2. And in this situation, what you do actually is to increase the gain on the brighter sides and decrease the gain on the darker sides. And therefore you can transform, for instance, this image into this image by applying this gamma correction. So the gamma correction can be particularly important when you are interested in give more importance to certain exposed, underexposed, or overexposed areas of the image.